we're now coming to the last but most important properties of probability. And these are looking at probabilities of unions. Remember that a union is OR. So this is what can we say about the probability of A or B? What's the probability that A happens or B happens or both, remembering that ORs are inclusive here. So there's something that we can already say straight away about unions, and that's if the union is disjoint. So if A and B are disjoint, which means they can't happen at the same time, then to get the probability of A or B, you just add up the probabilities. And you'll remember that that's just axiom 3. Axiom 3 was the probability axiom that said if you have disjoint events, then to get their union, you can just add them up. And so that's precisely what that theorem says. So what we're interested here is the more general result of what if they're not disjoint. So for any events A, B that might not be disjoint, and this is the result. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of them both. So, first let's have a little think about this result. You may have seen this result before, actually. If you have seen this result before, you probably justified it something like this. To get the probability of A and B, we want to add up the two probabilities. But if you think of the bit in the middle of the Venn diagram, the bit that's both of them, we've kind of counted that as part of A, but we've counted it as part of B as well. So we've ended up counting that intersection twice. And so we need to take it away again to make sure we're only counting it once. So that might be what you've seen before. And that's fine as like a way to remember the result or a way to kind of heuristically justify the result. But we're doing mathematics at university now, so we need to prove it. And we need to prove it just going from the axioms. And so it's no good to say, oh, we count this, but we've counted this bit twice, so let's take it away. We need to use just the probability axioms in order to prove it. So you'll remember that we said before, to prove things using the axioms, try and find a disjoint union. And so if we look at A union B, we see that that's not a disjoint union, right? If this box is the whole of omega, if we have A, and if we have B, in general, it's not a disjoint union, and it's not a disjoint union because there is an overlap. So what can we write that is a disjoint union? Well, if we start with A, it would be nice to say that A union B is A union something, but with this union on the right being disjoint. It'd be really nice if that were a disjoint union. So what does the other thing have to be? Well, it has to be the part of A union B we haven't coloured in, which is this bit of B that doesn't have the overlap. Right. So how can we describe just that bit there in blue, not counting the overlap? Well, it's the stuff that's in B and not in A. Right, that's what the blue stuff is there. It's the stuff that's in B and not in A. That's B and not A. B intersect A complement. So we've got the same thing on both sides of this, but crucially, this bit here is a disjoint union, which means we can use axiom 3. So let's do that. Let's see what's happened. See what happens. It might not prove the whole theorem for us, but we'll be getting somewhere. So this tells us that P A union B is equal to the probability of A plus probability of B intersect A complement. Well, we've made some progress here, right? If we look at the thing we were trying to prove to start with, both of them have got a PA union B on the left, And then both of them start with probability of A. But then it's this second term, this probability B intersect A complement, that isn't really what we want to be dealing with. So we're going to want to do something with this second term. So let's have a think about if we can find a disjoint union with that thing in. So let's draw the picture again. And B intersect A, as we said, was that set there. Is there another disjoint union that we can see involving this? Well, yes, there is, right? Because we don't just want to take the whole of A, because we just did that, and we're not going to get anything interesting by applying the same thing twice. If we then just take the intersection, then altogether that gives us B, and it's a disjoint union. Right, so we have another disjoint union hanging around here, which is that B is equal to B intersect A complement, that's the bit I've shaded in blue, union the thing shaded in green, which is A and B. So once again, this is true, but it's true with a disjoint union. So we can apply axiom 3 again. So let's do that. It tells us the probability of B equals the probability of B intersect A complement plus, applying axiom 3, probability of A intersect B. Now, if we look at what we had up here, the problem was this B intersect A complement term. So I suggest we rearrange what we've got at the bottom to make it probability of B intersect A complement equals something. So rearranging, it's probability of B intersect A complement equals probability of B minus probability A intersection B. So that's just taking the probability of A intersection B term over to the other side. So let me call that equation 2, and let me call the thing we had here equation 1. So we can substitute the value of P intersect A complement here from 2 into the value here that we wanted in 1. Right? So let's do that. Substitute 2 into 1. And that gives us, well, 1 is probability A union B equals probability of A plus. And then the thing that we had is the thing underlined in green that we've rewritten in 2, which is probability of B minus probability A intersect B. And that is what we were trying to prove all along. Right. Now that's quite a proof there. That's probably the most complicated proof we've done in the module so far. But I claim that every individual step of that actually wasn't difficult by itself. What we just did was on 2 occasions, we got our eye out to try and find a disjoint union. And then we found a useful disjoint union. We applied axiom 3 to it. The first thing was we wanted something about probability of A union B, so we found this disjoint union in the top picture. And then we had this awkward set B intersect A complement hanging around, but we found another disjoint union that involved that. And then by applying axiom 3 twice, we got what we want. So although that seemed difficult, there's actually no individual step that's hard, right? Look for disjoint unions, apply axiom 3. Now we've proved this union, this addition rule for unions, let's just do an example to show ourselves how we can use it. So the example is, let's imagine we're picking a card at random from a pack of cards. So omega is the set of deck of cards, which has 52 cards in it, and the probability measure here is the classical probability measure. All the cards are equally likely. So the probability of event A is the number of cards in A divided by 52. And we want to know what's the probability card is an ace or is a spade. Now, we could do this directly, just count up how many aces or spades there are in a deck of cards. And if you want to do it that way, you can do, and you can check whether we get the same answer here. But I'm going to use our new addition rule for unions here, which means that this is probability of ace plus probability of spade minus probability that it's an ace and a spade. Because that's our new addition rule for unions. So the probability of being an ace, you can either say that there are 4 aces in a pack of cards, so it's 4 over 52. Or you can say that there are 4 identical suits, each with 13 cards, one of which is an ace, so it's 1/13. Either of those is fine with me. Probability to spade, well, there are 13 spades in a pack of cards. There are 4 suits, each with 13 cards, so that's 13 over 52. The probability of an ace and a spade, well, there's only one card that is an ace and a spade. That's the ace of spades, and there's just one of those in the pack of cards. So that's 1 over 52. So 4 plus 13 is 17, take away 1 is 16, so that's 16 over 52. 4's go into both of those, don't they? So we could write that easier as 4/13. So the probability of getting an ace or a spade is 4/13. So that was an application of our addition rule for unions, which we used there. Just finally, you can also do addition rules for more events, which I've written down here. The first one is the addition rule for 3 events. So remember that for 2, it was we added the individual probabilities and then took away the double. Here, we're adding the individual probabilities, taking away all the double probabilities, and then adding the triple probability. You can prove this in the same way by writing down, these disjoint unions again, but I won't go through that here. In fact, an easier way to prove it is using the double rule first. And similarly, the thing that I've written down there is the inclusion-exclusion formula, like the general version of this, where again, you're taking all the individual events, and then you're subtracting all the double events, then you're adding all the triple events, and subtracting the quadruples, then adding the quintuples, and so on. And that's just the general rule. We mostly use this in the 2-event version, but if you ever needed unions of more events, then we've got this. Okay, so this whole section 2, has been quite a lot of theory stuff, a lot of proving things. And so next week in section 3, we're going to look a lot more at classical probability and do some old-fashioned calculating of stuff. And that should be a bit less theoretical. But that's the end of this section 2 on some of the theoretical properties that probability has.